Here's the solution to the Easter problem. So it's a conical barrel, has a 2-foot diameter, and it gives you some other information. It says that dH dt is negative square root of h over 10. And the volume is going to be pi r squared h. They've really gotten to where they like to give you the formulas. They're not really grading whether you know the formulas or not. They are grading whether or not you know how to work with the formulas. Now, just looking at this, we're not even talking about part A yet, but if we talk about doing the derivative of this, it's going to be the product rule. dv dt equals to 2 pi r dr dt h plus, then it's pi r squared dh dt. Now, that looks a little complicated at first until you think about the fact that the radius never changes. So when we have dr dt, that whole term becomes 0. So really, dv dt is just going to be pi r squared dh dt. All right, so let's get into the problem. The problem says that we want to find the rate of change of the volume of water in the barrel with respect to time when the height of water is 4 feet. So, we've got dv dt equals pi times 1 squared, so it's just going to be pi. Now, dh dt is the square root of 10, or I'm sorry, the square root of 4 over 10, which would be the negative pi over 5. And volume is in terms of cubic feet, so cubic feet per second. Those are going to be the units. So that is the solution to question number 1. All right, now question B, you got to be really careful with. It looks innocent enough as it is, but you've got to go into dH dt. So dH dt, and I'm going to rewrite this as negative h to the 1/2, and the reason I'm doing it like that is because they're asking us to plug in 3, and 3 does not have a perfect square, so negative h. All right, now it's not if the height's increasing or if the height's decreasing. It's if the rate of the height is increasing or the rate of the height is decreasing. So this is the rate of the height. So essentially what we're going to be looking at is the second derivative of height, or the derivative of the derivative. So d squared h over dt squared is, all right, it's negative 1/2, or 1/2 times, so we get negative 1 over 20 over the square root of h, because this would become h to the negative 1/2 here, and then dh dt. So d squared h dt squared is negative 1 over 20 square roots of h times, all right, dh dt is again the negative square root of h over 10. So now we can plug in the 3. Well, the 3's go away. So it's just negative 1 over 200. Positive 1 over 200. So we have a negative times a negative, so that number right there is greater than 0. Therefore, the rate of change height is increasing. So that's what we're looking at for the first two parts. Part 3 is the differential equation portion of the problem. And it's nice, they tell us, hey, we're going to use separation of variables. So dH over square root of h equals to negative 1/10 dt. Now this is also h to the negative 1/2 dh equals negative 1/10 dt. Okay, so from here we want to do the integral. So the integral here, you add 1, so it's h to the 1/2 over 1/2 equals negative 1/10 t plus c. All right, continue to solve it out. So I'm going to multiply both sides by 1/2, so h to the 1/2 equals negative 1/20 t plus a constant. Now square both sides, so h equals negative 1/20 t plus c squared. All right, now they tell us that at time 0, the height is going to be 5. So 5 will equal to c squared. So c is going to equal to the square root of 5. Now, it would not be the negative plus or minus the square root because you're not going to have a negative height here. So it's just going to be the positive square root here. Therefore, h is going to equal to negative t over 20 plus the square root of 5 quantity squared. That would be your height equation in terms of time. So hopefully that went well with you, and I will be shortly back with you with another problem of the day.